So today you're going to get an introduction on collisions. There's a PowerPoint that you're going to follow along with as we go over this information. We use this window to show you any of the math that we need to cover. In this PowerPoint there's a YouTube video you can click on. It talks about one of the collision types. So right now, open up that PowerPoint. It should be on the title screen. It says collisions. That's what the PowerPoint is about. So to start, defining a collision. A collision is when two objects or more impact each other. And so that's the big thing. Just an impact between two objects, and energy between the two objects is transferred, as well as momentum. And we're going to talk a lot about momentum today. But before we do that, I want to talk about what the two types of collisions are that we're going to focus on. So if you go to the next slide, slide number 3, we're talking about elastic collisions. So you can watch this video. I want you to watch the video right now, and then so go ahead and pause what I'm talking about, and then come back to this video that I'm making here after you watch the YouTube video. So now that you've hopefully paused the video and watched the YouTube video I've got on there, the big takeaway from elastic collisions is that both kinetic energy and momentum are conserved in an elastic collision. An elastic collision occurs when two objects hit each other and bounce off of one another, or one object that's stationary is hit by a moving object and that energy is transferred. This is the key takeaway. But the two things you need to remember are that both momentum and kinetic energy, not just energy, but kinetic energy, are conserved. So go ahead and go to the next slide on inelastic collisions. So an inelastic collision occurs when two objects run into each other and they remain stuck together. All right, in this scenario, momentum is conserved, but kinetic energy is not. Now, we'll talk about the conservation of momentum and what it means when we're talking about momentum being conserved, but it's important to understand that I'm specifying that kinetic energy is not conserved, not that energy isn't conserved. The energy gets dissipated in the form of heat and sound, and some of the kinetic energy is even conserved, except for not in the objects themselves. And the reason that kinetic energy isn't conserved, energy is conserved, but not kinetic energy, is the two objects can be moving towards each other, hit each other, and then just stop right there. So you went from two objects, each of which had kinetic energy, to one stationary object that no longer has kinetic energy. But the energy itself is conserved. The conservation of energy is still true, it's just not kinetic energy anymore. However, momentum is conserved in this scenario, and we're going to look a little bit more at the math behind why momentum is conserved in all collisions. So let's talk about what momentum is. So if you go to the next slide, the one that's titled momentum, you should see the equation for momentum, P equals mv, where P is the variable that stands for momentum, m is the variable that stands for mass, and v is the variable that stands for velocity. So what's important to understand is that this momentum equation works with any of the units. You could use standard units, you could use metric units, and you could use any of the metric units there are. However, for the purposes of this course, middle school physical science, 8th grade physical science, we're going to just use kilograms as our unit for mass, and we're going to use meters per second as our units for velocity. And as a result, the units for momentum, they're completely dependent on what mass and velocity units you use. The units for momentum that you're going to have are always going to be, in this class, kilograms times meters per second. And so you can see that's the combination of the mass unit as well as the velocity unit. So that's going to be your resultant momentum units whenever you solve for the momentum of an object. So basically all you're doing is you're taking the velocity of the object, multiplying it by the mass of the object, and you're going to get momentum. So next we're going to talk about conservation of momentum. So if you go to the next slide, you can see the definition of the conservation of momentum. But momentum is the combination of an object's mass and its velocity. And really the key is the larger the mass of the object, the larger the momentum, the larger the velocity of the object, the larger momentum. So a really massive, slow object, like a train, can have a lot of momentum because it has so much mass, even when it's going slow. That means it's really hard to stop. Conversely, you can have a really small object, something that doesn't have a lot of mass, but has a lot of velocity, like a bullet, and that will also be very difficult to stop. So momentum is really an object's propensity to continue going at the same velocity that it's in. And this all relates back to Newton's first law, which, as you should know, is an object in motion will stay in motion unless acted on by an outside force, and an object at rest will stay at rest unless acted on by outside force. So an object's propensity to stay in motion is momentum. And so the conservation of momentum says that in a system, the momentum of all the objects, when you take the sum of those momentums, will always be conserved. All right? So conservation of momentum in a system, just like conservation of energy and conservation of mass. In a closed system, the momentum of all the objects will be conserved. So that is the conservation of momentum. Remember from the definition that's on the slide. And right now, that's the end of the slideshow. But I want to show you a scenario. We're going to look at two things. Number one, how to calculate momentum of an object. And then also, we're going to look at calculating the momentum in an inelastic collision. We're not going to focus on elastic collisions this year. The math is a little bit complex, but calculating the momentum of an object is really easy, as well as calculating the momentum of an object after an inelastic collision. So let's go ahead and get rid of these units. You should have them written down by now, I would hope. And we're going to look at an object, okay? Let's say we just have an object, okay? And it's moving to the right. It has a velocity of 5 meters per second. And the mass of the object, let's just say it's 3 kilograms, all right? So I want to know the momentum of this object. So you're going to take the equation, P equals mv, where our mass is 3 and our velocity is 5, and we're going to solve for p. Now obviously 3 times 5 is 15, and so that's the takeaway. Our momentum of this object is 15, but of course we need our units, which are kilograms times meters divided by seconds. And so that was how you calculate the momentum of just one object. So this isn't a collision or anything, it's just an object that's 3 kilograms moving to the right at a velocity of 5 meters per second. Its momentum would be 15 kilograms times meters per second. Now, let's look at an inelastic collision and the equation that we're going to use for that. And we're going to say that we have two objects now, okay? We're going to have an object that is also 3 kilograms, but this object is going to be moving to the right at 10 meters per second, okay? So you should see that this object that's on the left is going to catch up to the object that's on the right eventually. And so because it's an inelastic collision, these two objects should stick together and continue traveling as one after this collision occurs. And we want to calculate the velocity that they're going to go. So check out this equation for conservation of momentum in an inelastic collision. The equation is m1 v1, which this stands for the mass of the first object times times the velocity of the first object. That should give us the momentum of the first object. So plus m2 v2, and now we're talking about the mass of the second object times the velocity of the second object. So this should give us the momentum of the second object, equals m sub f v sub f, which is the mass final and velocity final of the object. Now, what we're seeing here is in an inelastic collision, we have two objects that come together and stick together. And in essence, those two objects become one object, which is what we're talking about here. So this is how we're going to plug in the values. This is just an example of how to plug the values in for an inelastic collision. Let's say that the object on the left is our first object. And it doesn't really make any difference because of the associative property of addition. But we'll just say this is object 1. The mass is 3. The velocity is 10. All right? And then that means our second object will be the one on the right here. It's going to catch up to and stick to. So the mass of this object is also 3, but its velocity is 5. So now we've got m1v1 plus m2v2. So this is the momentum of those two objects. And because of the conservation of momentum, the momentum after the collision should be equal to the sums of the two objects' momentum. So we can fill in part of this, the mass. We don't know the velocity yet. And the reason we know what the mass is because these two 3-kilogram objects are going to stick together to become one object whose mass obviously should be the sum of the two masses of the object. So 3 plus 3 is 6. So that's going to be our M final. But what we don't know is what our V sub F, or V final, will be. And that's okay because it's the only variable we haven't solved for in the equation. So what we're going to do is we're doing the math. 3 times 10 is 30, and then 3 times 5 is 15. 30 plus 15 is 45. Equals 6 times V. And now we need to solve for V. And to do that, we got to divide both sides by 6. And you might want to use a calculator. But when you take 45 and divide it by 6, what you end up with is 7.5. So our velocity of this object after the collision is 7.5 meters per second. And so, because of the conservation of momentum, if we have two objects that are engaged in an inelastic collision where they stick together like this, then we can calculate the velocity of those objects after the collision occurs. So I want to talk about velocity really quick. It's important to understand velocity is a vector measurement. This you should have talked about vectors and scalars. The vector measurements have both a magnitude and a direction, which means that there's a positive direction of movement and a negative direction of movement. In a scalar measurement, there is no direction, there's only magnitude. So like speed is a scalar measurement. It doesn't matter what direction you're traveling, you will have a speed and it will be a positive number. However, velocity is a vector measurement. So that means that you'll have both a speed, a magnitude, and a direction. And if that direction is in the negative direction, then you'll have a negative velocity. And the reason this is important when it comes to the conservation of momentum is, these two objects, they're traveling in the same direction. So they both have positive velocities. And then the outcome is a positive velocity. But you could also have an inelastic collision where there's two objects moving towards each other. And one would have a positive velocity component, the other one would have a negative velocity component, and those two velocities cancel each other out. So it's important to remember that because velocity is a vector measurement, that there's both a negative and a positive component that you could have. And it all depends on what you call positive. In this scenario, because these are both positive, then obviously if an object's moving to the right, its velocity is positive. However, if the object had been moving to the left, its velocity would be negative. So this is how the sorry about that. This is how conservation of momentum, this is why velocity is important for conservation of momentum. And last thing I want to talk about is elastic and inelastic collisions. There's no such thing as a perfectly elastic collision, and there's no such thing as a perfectly inelastic collision in the real world. See, to have an elastic collision or an inelastic collision, when the objects strike each other, there could be no deformation. Because when objects deform, when they strike each other, that is losing energy to the object's deformation. It's not just a perfect bounce off of one another. Now, these inelastic and elastic collisions and the math that goes behind them provide really good insight into collisions between objects in the real world, but it's not a perfect simulation using mathematics. And you know that objects deform when they run into each other because you probably have seen in the past slow-mo videos of like a baseball bat hitting a baseball, or maybe a golf club hitting a golf ball. And in those slow motion videos, you probably saw the ball deform into an ovular shape, or maybe the bat even bend when it strikes the ball. And so that means there's not a perfect transfer of momentum or a perfect transfer of that kinetic energy between the two objects. And so if you were to look at those scenarios, you'd see that the collision wasn't a perfectly elastic collision. Or if two cars were to run into each other and become entangled with one another, of course you're going to see the two cars, they're going to deform. And so once again, even though the two objects are stuck together after the collision, that's not a perfect example of an inelastic collision. Because in a perfect inelastic collision, the two objects should stick together but not deform at all. That being said, we can still use these equations to simulate and model those scenarios, even though they're not perfect. And finally, what's important to remember is that even though there's no such thing as perfect inelastic and elastic collisions, that doesn't mean the conservation of momentum isn't true. Momentum is always conserved. Momentum is always conserved, even if the collision isn't a perfectly elastic or perfectly inelastic collision. So those are the big takeaways. Make sure you got all the information down from the slides. Make sure you got a good understanding of the math we talked about for momentum, as well as the equations for inelastic collisions. And remember, momentum is always conserved.